A bar of length L and weight W is supported by two gliders connected by two cables and a spring of stiffness K. Initially, the bar was held in a position so that its incline angle was equal to alpha. We need to determine the equation for the incline angle once the bar is released. As usual, I will begin with drawing free body diagrams. My first free body is the bar attached to the gliders. I show the weight of the bar, and I recognize that the glider is constrained by a cable, and also the glider is constrained by the channel, and since it's smooth, I will show just a normal force. This force must be up because the cable is a unilateral constraint, but this force could go either way, right? We can have this side constraining the glider or this side constraining the glider. In a very similar manner, I deal with the second glider. I show the force corresponding to the constraint imposed by this cable, and I show a normal force exerted by the channel. Next, let me look at the free body diagram that involves the wheel and two pieces of cable. The wheel is constrained by the pin, and therefore, as I remove the pin, I produce two forces. Then the cable is constrained by the lower part of the cable, and it is shown by this force. And I show this force in green to indicate that this force is the force that the lower part of the cable exerts on the upper part of the cable. Here I have a force exerted by the upper part of the cable on the lower part of the cable, and by the third law, these two guys are equal in magnitude and opposite in direction. Finally, I will show the force associated with the constraint imposed by the part of the cable to the right of the pulley. Finally, I will show a free body diagram for the spring. Both forces are in green because this force and this force are related by the third law, and so is this force and this force. Now let me do a quick count of equations and unknowns. The unknowns are blue forces. I have 4 here, and I have 3 more, so the total count is 7. I have 3 free body diagrams, which will give me 9 equations, but the free body diagram for the spring will produce only one non-trivial equation, sum of the forces on X, and therefore I have 7 equations and 7 unknowns, and I'm in a good position to proceed. First, let me look at the pulley and write down some of the moments about C. This equation, as usual, will tell me that T1 is equal to T2, and I simply call these forces T. And I'm not going to write the force equilibrium equations simply because I'm not interested in calculating the forces Cx and C1. Also, I can quickly recognize that since the force T2 is equal to T, then the equilibrium of the spring simply says that the spring is stretched by two forces T. With this in mind, I can proceed to the final free body diagram, and here I show the forces T and T and the weight. And again, I will economize things a bit, and I will draw a line that coincides with this horizontal force and a line that coincides with this vertical force. The intersection of these lines is D, and I would like to write down some of the moments about D. The reason I choose this point is because this force and this force are not engaged, and therefore some of the moments reads the following. T produces a clockwise moment, and the arm for T is the length of the bar times cos beta. For W, the moment is counterclockwise, and the arm is half of what it is for this T. Finally, for this force T, the arm is L sine beta, and the moment is counterclockwise, and we obtain this equation, which allows us to calculate T in terms of W and beta. Now we are done with equilibrium equations, but we still need to find the angle beta. To find the angle beta, I need to exploit Hooke's law for the spring. Let me remind you that Hooke's law is written in the form T equal to K delta L, where K is the spring stiffness, which is known, and LF minus LE is nothing but the difference between the final and initial length. To find LF, I observe that the lengths of the spring plus the lengths of the cable have to be equal to the sum of the cathets in the right angle triangle, and that triangle is associated with the angle beta. The same sum, but for the initial lengths, could be expressed using the angle alpha. Now what we can do, we can substitute LF found from this equation and LE found from this equation into this expression. What we will find that L sub C will cancel each other out, and if we combine the right hand side and T found from equilibrium, we obtain the following equation for the angle beta. I want to pay your attention that the dependence on alpha is somewhat involved. It sits right here. However, the dependence on W, K, and L is reduced to a single parameter. So what this means is the following, that three independent parameters, W, K, L, are collapsed into one dimensionless parameter that can be used to characterize the entire system. Thank you.